So believe it or not, actually, no, you don't get a choice there. You have to believe it. Electricity comes from chemistry. Now we think of chemistry as things burning, things melting, things changing color, but actually there's more to it than that. And electricity is one of the facets of chemistry. And if we look at the word electrochemistry, well, electrons, electricity, yeah, they're all dealing with the exact same thing. So anything that's electrically powered, especially things that are battery powered, so cell phones, laptops, Walkmans, all of those are running on a chemical reaction. A chemical reaction that moves electrons, and the moving of electrons causes electricity, which we then harness and use to power things. And the movement of electrons, we go back to redox. So if we think back to when we first talked about redox, remember that oxidation is loss and reduction is gain. And what we're referring to there is electrons. So something that is oxidized is losing an electron to something that is reduced. And that movement of electron from one object to the other then, if we were to put a wire in between these two objects right here, so a piece of copper wire, cause the electrons to flow through that wire right there, then we could put anything in between right here, be it an iPod, a cell phone, a laptop, and we can power it with those electrons as they flow from one thing to the other. And we call this process right here electrochemistry. Different types of batteries, different strengths of batteries, just depends on what we put here and what we put there. So let's talk about some of the properties of electricity. If you think back to freshman science, voltage, current, and resistance were the three that you learned there. Current's going to be the main one that we focus on in chemistry. And so current is the amount of charge that passes through a cross-sectional area of a medium per second. So what does that mean? Well, if you have a wire and we were just to look at a cross-sectional area, so just like a thin line, just observe right there, it would be how much charge passes through that point per second. The thickness of the wire, kind of the push of the electrons, all of those are going to make a difference in the overall electrical current. And so current can be measured in amperes or amps, which we symbolize with a capital A, and it's equal to the charge of the stuff that's going through. In this case, it's going to be electrons. And charge is a fundamental property like mass would be, or momentum. And then it's going to be divided by time seconds. So it's how much charge passes through a point every second. And then for stoichiometry, we have Faraday's constant. And Faraday's constant is equal to 96,500 coulombs per mole of electrons. And coulombs is just the measurement of charge. And so this gives us a way to relate charge to actual electrons. And it's worth noting all the units on this real quick because there's going to be a couple conversions. So amperes, a lot of times you're going to be dealing with milliamps, and so you got to make sure that for the unit you're using the regular A, and then coulombs C, and then time has to be in seconds. It's not very often that we measure time in seconds. A lot of times it's going to be minutes or hours. You need to make sure that you always convert to seconds. And this brings us to something that ends up being strangely confusing a little bit later on, and that is the idea that the units for current, which are amperes or A, is really saying the same thing as charge per second. Okay, think of like molarity. Okay, molarity is M, and in order to calculate molarity, we divide moles per liter, and so that means the units for molarity are really moles per liter. So amperes, the same thing, we're dividing charge by seconds, and so that means that the units for amperes is really the same thing as saying coulombs per second. So if we have something that's 5 amps, okay, that's really the same thing as saying there is 5 coulombs per 1 second passing through that cross-sectional area. And the reason this idea is important is the same reason this idea is important. When we do stoichiometry, we need those derived units like this so that we can cancel things out. Using just a capital M doesn't always work very well, but having a mole and a liter so we can cancel something out works really, really well. Having just an A is okay for a final answer, but sometimes we need to cancel out coulombs or seconds, and so we would need to remember this little fact right there. So let's do a practice problem then. So how much charge passes through a cross-section area of a wire that is carrying 0.987 amps of current for 12.3 minutes, and then how many moles of electrons would that be? Now you can go back and you can use that equation that we just saw, but that should be fairly simple. I'm actually going to show you how to do this the stoichiometry way, which is going to be a much more valuable technique to have in your belt. So in this case, 0.987 amps of current. Remember, 0.987 amps is the same thing as 0.987 coulombs per 1 second. And in this case, we have 12.3 minutes. We never start with a conversion factor, which is what that would be. We'd want to start with something that's not a derived unit, so just 12.3 minutes, and then set up our stoichiometry from there. Now 12.3 minutes, we can't use that with our amperes. We've got to convert that first. And so there is 60 seconds for every 1 minute. And that cancels out minutes, leaves us with seconds. So now we can throw our amperes in there, and we can say there's 0.987 coulombs for every 1 second. And so then when we solve this out, we would see that there would be 728 coulombs that would pass through. And so that would be our final answer for that one. And now to find the moles of electrons, we have 728 coulombs, and this is where that Faraday's constant comes in. So Faraday's constant says that for every 96,500 coulombs, you have 1 mole of electrons. So for every 96,500 coulombs that go through a cross-section area, 1 mole of electrons would have passed through. And so then that would mean that 7.54 times 10 to the negative third moles of electrons pass through. Now you notice how these two questions flowed one from the other. First we calculated the 728, then we used the 728. You're not always going to be asked an A-B version of this question. Sometimes you might just be told this information, then asked how many electrons pass through that cross-section area. In which case we could have done this as just one solid problem by multiplying this right up there and give us this final answer.